Okay, another problem going in. This is the Atwood's machine problem, so go ahead and properly name it Atwood machine. Okay, so check this out. It says, given the system of masses, three masses, determine the acceleration of the mass m1. One thing to note is that this is a frictionless pulley. If it wasn't frictionless, then the way that we're doing it would not apply. So careful. So m1 is 30 kilograms. M2 is 15 kilograms, and M3 is 5 kilograms, just writing it in there. And we can approach this several ways. The first way that I'm going to approach it is going to be the longer way. Skip a few minutes ahead if you did the shorter way. And that's the approaching it as a system. But right now, let's go to approach it as individual pieces. Each piece will have their own free body diagram. And again, if you're stuck, if you don't know what to do, then it's always good to just go back to the basics and draw a free body diagram for every single object that you have. And so here are our three free body diagrams. We have 300 newtons going down here, mg, 30 times 10. Mastering physics, use 9.8. Over here, 15 is going to be 150, and we have 50 over here. And one thing that I forgot to draw over here was actually there is a force of tension pulling down here. So while this is a tension pulling up, that's a tension pulling up, that's a tension pulling up, this is a tension pulling down. We need to number these because they are not the same. Let's call this in T1, same rope, T1, and different rope, T2, and there you go. So these two tensions would be the same. Newton's third law says, hey, if we have a force, we have an equal and opposite reactionary force, and there you go. That's where it is. So looking at this whole thing, this side is more massive than this side, and it's probably going to rotate or accelerate in this direction. I'm not going to say it's going to rotate that way because we can rotate any way we want. It's just going to be speeding up or slowing down. So the equation for the right side is going to be picking clockwise as positive and counterclockwise as negative. It's going to be 300 minus the force of tension T1 is equal to m, the m that we're talking about, times a. Okay, that's the first equation that we're going to write. Over here, we're going to say that clockwise being positive, these tensions will be positive, the T2s, and this T1 and T2. T2 minus 50 is equal to MA, or 5A. For this equation, we'll say that the tension T1 minus 150 minus T2 is equal to 15A. Okay, do you see what I did? So for each of these equations, I just looked at that one object, or that object, or that object. I didn't care about all the other ones. I'm just drawing my free body diagram for that one object. So looking at this, we have an equation for T2. T2 is equal to 5A plus 50. And that's going to be useful because that's where we have T2 up here. T1 minus 150 minus T2, which is actually 5A, and I'll go ahead and distribute the negative over because it would be in parentheses in the first place, equals 15A. And let's see, I have things that are in common. T1, again, minus 150 minus 50 minus 200 minus 5A is equal to 15A. And I'll move that 5A to the other side. T1 minus 200 is equal to 20A. All right. So really, what this just proves, I know this is a long way to go about it, but it's like saying, hey, these two masses, they're on the same side. We can combine them. It's 15 plus 5. That's going to give you 20. The whole force there would be 200. That's going to be fighting a tension T1. T1 minus 200 would give you a MA of the combined 20A. Okay? And so we have an equation. T1 minus 200 is equal to 20A. And we could have gotten this from the very beginning. If we just said that these two objects were just one object of 20 kilograms of mass, and so there's T1 pulling up, and there's a force of gravity 200 pulling down, and that equals ma, and that's fine. Just going long about it. The other equation is 300 minus T1 is equal to 30A. Okay? And I look at these two things and I can do substitution. With this problem, I like to do addition, just adding the equations together. So I'm going to take one equation and I'm just going to plop it down underneath the other equation. And we're going to add the right side. We get 50A. We're going to add the left sides. T1 and negative T1, 0. 300 minus 200 is equal to 50A. That's 100 is equal to 50A. Hey, what's A? It's got to be 2. And there's your solution for this one. Now I'm going to go back and do the systems way. And for you guys that did the systems way, I'm going to write out really big systems. And so people that are fast forwarding can say, hey, systems. Okay, so to do it as a system, we're going to look at it as one big moving thing. So how much stuff is in our big moving thing? We have 30 and 15 and 5. That's going to be a total of 50 kilograms of stuff. So as a system, our mass is 50 kilograms. Okay? And so we're going to look at our external forces and we're going to look at our internal forces. So internally, these are forces that are going to cancel themselves out. And so if I look at my picture right now, I've got tension 2 going up and I've got tension 2 going down, and that cancels out. I have tension 1 going up and I have tension 1 going up the other way, but they're pulling against each other if it goes around this curve, so those two cancel out. Okay, so those are internal forces. The external forces here are going to be gravity. Gravity on the right side is 300. Okay, that's making this thing rotate clockwise. That's 300. On the other side, we have a total of 200 newtons of force from gravity, trying to make it go the other way. Who's going to win? Well, external forces, the sum of all forces external, is going to be equal to 300 for the force of gravity on the right side minus 200 for the force of gravity on the left side, and that gives us a total force of 100 newtons left over. So 100 newtons is what's trying to rotate this thing in the clockwise manner. If 100 is our force, force is equal to ma. How much m are we trying to move? That's going to be 50. So A would have to be 2 meters per second squared. And that would be the quick way to do it. So some people's brains work like this. They like the individual steps. They like to see everything. Others, they just want to look at it as one big picture and get it done fast. Just don't screw up. All right, there's that one.